We take up this problem number 84 of your textbook. It says that a solid sphere of mass 0.5 kg, mind it, it's a solid sphere. So the moment of inertia is 2 by 5 mr square. The sphere is kept on a horizontal surface. So actually there is a solid sphere. There is a solid sphere kept on a horizontal surface. The coefficient of static friction between the surface and the contact is 2 by 7. So mu is equal to 2 by 7. What maximum force can be applied at the highest point in the horizontal direction so that the sphere does not slip on the surface? That means at this point, a force is applied, say force F. What maximum force can be applied? That is the question. A sphere has a mass of 0.5 kg, so its mass is 0.5 kg, and the radius is not given. Let us say radius is r. Now look at the problem. If we apply the force F gently, I mind it, I said gently, then it will start rolling like this. But obviously, if the force is too high, then it will roll as well as it will start slipping. That is very obvious. Now the question is, given a value of mu of 2 by 7, what is the maximum value of this force? Now, let's say this point of contact is P. Right? Say the point of contact is P. Say the point of contact is P. Obviously, if there is a dragging, then P will be dragged in forward direction. P will be dragged in forward. If there is a dragging, then if there is a dragging, so when it is rolling, I erased everything. This point P moves in the backward direction. Say the point of contact is P, which moves backward to rolling. Which I think this is obvious to you. This point P, when it starts rolling, this point P, which is a point of contact, will move backward. Therefore, if there is a dragging, the frictional force works in forward direction. So if there is a dragging, if there is a slipping, the frictional force acts in forward direction. In forward direction. So this is the frictional force. That means if you now consider the free body diagram of this sphere, there are two forces acting in the same direction. One is capital F force we apply and the frictional force F. Frictional force F. And say eventually the body center of mass, the body moves towards your right and say it has got an acceleration ACM. Then obviously from the theory of kinematics, the sum of the two forces, so capital F plus small f, will be equal to its mass multiplied by linear acceleration of the center of mass. This is, we mark it as equation 1. Now consider rotation. Now consider rotation. Now consider, if we consider rotation, then F applies a clockwise torque, at small f applies the anti-clockwise torque. So, of course, for rotating, capital F has to be more. So the net torque is equal to capital F minus small f multiplied by the radius arm. This also has to be equal to moment of inertia I into alpha, where alpha is the angular acceleration. Alpha, say this is angular acceleration is alpha, and linear acceleration is ACM. This alpha is nothing but, alpha has a relation with ACM. So alpha is equal to ACM by R, right? So F minus F, from here we get capital F minus small f is equal to I ACM, moment of inertia of I, ACM divided by R square. I is the moment of inertia of the solid sphere, is 2 by 5 mr square by 5 mr square multiplied by ACM by R square. This R square gets cancelled. So what we are left with is 2 by 5 MACM is equal to 2 by 5 MACM. This is F minus F. Also, we have found F minus F in equation 1. So combining equation 1 and 2, combining equations 1 and 2, what do we get? Combining equation 1 and 2, we get capital F minus small f is equal to by 5. So we have found capital F minus small f here. We have got capital F minus 2 by 5 is equal to, from MACM, MACM is capital F plus small f. So capital F minus small f is equal to by 5. MACM is capital F plus small f. Capital F plus small f. From there we find 5f minus 5 small f is equal to 2 capital F minus 2 small f. From there we find 7 small f. 7 small f is equal to 5 minus 2 is equal to 3 capital F, or which is equal to capital F, because they wanted us to find out the value of capital F. Capital F is equal to 7 by 3 small f. This is relation 3 we have got. So we have got a relation between capital F and small f to ensure pure rolling. Now they wanted us to find out what is the maximum value of capital F. So naturally we have to apply the maximum value of small f, right? So I write it this way. The question wants to find maximum value of capital F. So we use maximum value of small f, which is equal to maximum value of small f is equal to n mu, or here n is m, g, and multiplied by mu, mg. So the relation now becomes, this relation from relation 3 we find capital F max equal to 7 by 3 small f max, which is equal to 7 by 3 mg mu is equal to 7 by 3, m is given 0.5. Mass of the sphere is given 0.5, multiplied by g we consider 9.8, mu is given 2 by 7. If you calculate this with a calculator, you will find it is 3.27 Newton. And so this is the answer they wanted you to find out. So maximum force that can be applied here is 3.27 Newton. If you apply a larger force, then what will happen? It will of course rotate, but at the same time, it will drag the sphere over the surface, because the frictional coefficient will not be able to produce enough friction to stop linear translation. Right? We now go to the next question.